to all of you. Today it is going to be the seventh session of webinar on CA. So next is Professor Nadim Fair's talk that is scheduled on 30th of January. Actually, I did a mistake in swapping these two talks. So probably you have got the invitation of that talk earlier. So I will just like to announce that on 30th, Professor Nadim Fetz will give a talk on does robust computation exist? Some reflection on asynchronous and probabilistic CA. And today's talk is ambiguity and computability in complex cellular automata. We are very pleased to have among us Professor Gennaro Martinez. He is in the morning itself. He has given us time, so nice of. So Professor Martinez is a full-time researcher at the National Polytechnic Institute in Mexico City. He is an active member of several institutions and laboratories around the world, such as the International Unconventional Computing Laboratory at the University of West England in UK, Foundation of Computer Science Laboratory in the Hiroshima University, Japan, Center for Chaos and Complex Networks at the City University of Hong Kong in China, Unconventional Algorithms and Computing Lab at the Technical University of Ostrava in Czech Republic. Then some other institutes are also there where he is the member, an active member and researcher there. He he is also the member of editorial board for several reputed journals, just like Journal of Cellular Automata, Complex System, Physicality, International Journal of Bifurcation and Chaos, Artificial Life, Nonlinear Dynamics, Information Science, IEEE Transactions on Circuits and Systems, and so on. Professor Martinez, together with Professor Adamski, has published a book, Designing Beauty, The Art of Cellular Automata. This is a beautiful book indeed. And he is also leading two computational paradigms in cellular automata theory, collider cellular automata and computation by computing patterns with cellular automata. Along with that, he is also interested in several social services that I recently came to know, but I'm not elaborating here. So it's so nice to have you here as our speaker. Over to you, sir.
Okay. Thank you very much for the introduction. And thanks to organizers for inviting me to give this talk. For me, it's an honor to stay with you and take time for know more the cellular automata community in India. And I have a special interest for the work of Professor Sukanta for several years. And I will start the presentation. Okay, I will share my slides. It's okay?
Yes, okay.
Yeah, okay.
Yeah.
Okay, thank you.
Thank you.
All right, the subject in this talk is discuss some subjects about of ambiguity and computability in complex automata. This research has several years ago, and I have collaborations from several students and researchers around the world that are concentrated into laboratories that I handle in Mexico City, from Mexico City. So what is the question here? We have interest in know what happened with complex behavior, mainly in cellular automata theory. But the complex systems is a very old subject where we have real antecedent with the Mason conference. And we will discuss what happens if you use a kind of memory function in cellular automata where this kind of dynamical systems can change to other dynamics. Okay, I have a special interest in the Macy conference because the complex systems theory discusses several kinds of initial states. However, the Mason conference has discussed this idea of interdisciplinary subjects, where we can see several kinds of researchers together discussing relevant problems in the post-war time. Here we can see very famous researchers as McCulloch, Pitts, von Neumann, Shannon, Norbert Wiener, Rosenbluth, and so on. So if we look with attention what happened in this conference, some subjects are related here. For example, the subjects about of nonlinear problems, systems theory, cybernetics, cognitive science, and in this moment, a lot of questions emerge in these meetings. For example, what does information and what represent this one in computation? And later, how we can relate this kind of information in living organisms. That is how works the nature. The other one is how some artificial systems are related to these living organisms. For example, the automata theory or finite state machines theory. Later, if we are able to recognize complex behavior, how these systems could feedback a kind of information or other problems. In particular, the Macy conference are related for the first academic transdisciplinary exercise. Well, why consider cellular automata's theory? My main motivation comes with two directions. The first one comes with Edward Fredkin, because Edward Fredkin wrote an interesting paper in 1982, The Finite Nature, where he conjectured that the problem in nature and the universe could be related to a discrete system. So for discuss how these very big problems can be represented in a system, he considered the cellular automata theory, where is a discrete dynamical system, and how in a massive computing process, he can explain several of these ideas. The second motivation comes with Stephen Wolfram. Wolfram wrote a book in the year 2022, and it's a controversial book. This is a new kind of science. But the main interesting question here is, how do simple programs are able to produce complex behavior? And this question is discussed many times with several kinds of cellular automata rules. And it's really very interesting how these small and simple rules are able to produce complex behavior. Of course, the other motivation is how these simple rules are able to control computable systems. Time ago, Harold McIntosh has discussed that cellular automata have influence stage. Okay, the first one comes with John von Neumann, the precursor of cellular automata, because he discussed the problem of universal constructors, how a system is able to handle universal constructor that is possible to construct the whole universe. At the same time, he discussed what is the situation with the self-reproduction problems and universality. The second stage can be considered by John Orton Conway, because John Conway present the game of life, so two-dimensional cellular automata, that maybe it's the most popular cellular automata around the world. And he present a system of gliders working in two dimensions and how these complex structures emerge and interact in the space. Of course, Conway discusses the problem of universal systems in the game of life. The third stage could be with Stephen Wolfram, because Wolfram in the 80s years establishes the problem of cellular automata in one dimension. Also, he presented a classification of these systems and start a computable analysis or systematic analysis in cellular automata. The last one could be considered with Matthew Cook, because Matthew Cook proved that the most small and simple cellular automata is able to universality. And he proposed another kind of computable system, that the cyclic tax system. And it's very interesting how he obtained this result. Okay, cellular automata are discrete dynamical systems evolving in an infinite regular lattice. This one can be represented for algebraic structure where we have finite alphabet, a local connection that is referred common as the local rule. The local rule considers a central cell and neighbors around of it, and it is named as a neighborhood. So consequently, the local function establishes a relation between these neighborhoods with an element of the alphabet. So, as any automata theory, we need an initial condition to study the system. So, a consequent relation with this theory is the global transitions between configuration. That is another kind where you can see or explore the universe in cellular automata theory. Okay, what happened with this global relations? Well, in 1984, Stephen Wolfram defines a classification for basically in elementary cellular automata, that is automata in one dimension. And Wolfram establishes that all cellular automata can be confined in 4 classes. The first class is the trivial behavior in cellular automata, because regularly the evolution is reached in very few states, and you can see any activity in this kind of cellular automata. Class 2 relate the periodic behavior, where fragments of configurations repeat every time and forever, and these types of rules. Class 3 concerned to chaotic behavior, where we have not some method to recognize patterns of some kind of behavior in the evolution space. The last class is the class 4, where it's related to complex behavior, because initially it is a mixture of the other class, plus complex patterns emerging in the evolution space. Here we can see some examples with Cellular Automata classes. One dimension, that is the first evolution. It is a typical rule where you can select different random initial conditions, but in few steps, you will reach the stability of the system. In this case, is only one state. The second example represents class 2. Class 2 is the periodic behavior, and this is a two-dimensional Cellular Automata with, I think, 3 or 5 states, where, again, you can start with a random initial condition, but the time will show a periodic behavior. In this case, it's a propagation of waves, where these waves are dominating the evolution later of some steps. Chaotic behavior, it is a three-dimensional Cellular Automata where the space is dominated quickly for a population of cells that don't show any particular pattern. So the last one is class 4. It is the famous the game of life, because starting from random initial condition, you can see how a lot of chaotic regions fight to preserve the space. Other regions are uniform, but others are stable with periodic patterns in this region. But at the same time, we can see how emerge some not trivial patterns are particles or gliders that are related frequently in the cellular automata theory. So the interesting thing here is how these patterns interact with behavior. That is, then we have a classification of these classes from uniform, periodic, chaos, or complex. However, for several years, this classification is studied for several techniques using, for example, probabilistic approximations that Hector had discussed, I think, 3 presentations ago. And in the same case, this problem is recurrent because, for example, in the periodic class, we can distinguish between pseudo-periodic classes and periodic classes. I remember the work of Chatet and Maneville in the 18 years, where these French researchers proved that a kind of cellular automata are able to produce the pseudo-periodic classes. Then, what is the limit between periodic and pseudo-periodic class? In chaos theory, we have the same problem, because actually you can see three levels in chaos: the hard chaos, the chaos, and weak chaos. But the problem again is the same. what is the limit between these classes? So it is hoped that we will see the same problem in the complex class. Okay, in 1988, Kulik and Yu proved that the classification to obtain complex behavior is an undecidable problem. It is not good news for you because an algorithm to represent this classification is not available yet. Okay, I remember some discussions with Harold McIntosh. McIntosh commented several years ago, if you watch the evolution of an arbitrary linear automaton from a random initial configuration, implies to see a great deal of confusion. That is what happened in the evolution. No? Well, actually, we can conclude that no classification serves to classify complexity. In this paper published in the Journal of Cellular Automata, we explore several classifications, and none of them overlap. That means all they are different to represent classes in Cellular Automata. Okay. We will concentrate our attention in elementary cellular automata, and we will remind the Wolfram's classification, where he specified that 4 roles in elementary cellular automata are complex, right? So the most high density for a kind of class is the class 2, periodic class, and later the chaotic rules, and finally the uniform rules. Well, particularly Rule 54 and Rule 110 has captured special attention for complex behavior and the capacity to implement algorithms in this class. In the other case, we can see, for example, the Wenshi classification, where he classified those rules given the symmetric properties in the local rule. This way, we can see 3 classes of set of rules. However, this classification don't give you many information about of what is the dynamics in these rules, right? Indeed, we can see a mixture of dynamics in these classes. However, of course, this study was very useful to simplify the number of rules in elementary cellular automata, because here we have 256 local rules, but across of this study, the rules are reduced to 88 equivalent local rules, right? However, we can see some very specific classification in elementary cellular automata. For example, Harold McIntosh and Juan Carlos Seck determines that the rules for bijective and surjective rules are in 2 specific classes, right? What is the interest of this classification? Is identify the reversible cellular automata. Reversible cellular automata in elementary cellular case is the rule 15, 51, 170, and 204. The other interesting rules are the surjective rules. For example, Rule 30, that is very popular for Stephen Wolfram, because Rule 30 is used to cryptography applications, for example. But it's very interesting how these rules evolve, and they always have ancestors to continue the evolutions. So in this case, and particularly the concept of the Garden of Eden here uh, is not related in these evolutions. Indeed, Sukanta Das and students in college in India have proposed interesting classifications of cellular automata. In this paper, they discuss how if you compose some local rules, you can produce reversible behavior in this elementary cellular automata. It's very interesting because indeed, several rules in elementary cellular automata have degrees of reversibility properties. For example, the rule 45 is classified than chaotic rule by Stephen Wolfram. However, this rule has the property of reversibility, because if you analyze this evolution for the length of the string for odd or even number, you can discover reversibility properties. So it is very interesting how this composition of rules produce reversible behavior. Okay, I will put special attention for a work that David Epstein has specified several years ago, discussing this Wolfram classification. Epstein say that class 4 can be characterized by evolutions with complex structures emerging in the evolution space. But how these complex structures live for a long time in the evolution space. So this is a criteria where Epstein start classification in 2 dimensions. But it's very useful because this restriction determines maybe with most clarity what is the implication of complex behavior. At the same time, a lot of techniques are used to classify or recognize complex behavior. For example, the main field approximation is a polynomial that study what is the frequency where number of state is in the evolution space, and the frequency is related to the local rule, because the local rule determines what is the probability to get this value in the next generation. So it is a good approximation because the number of fixed points in the curve specify if you can recognize a stable behavior or unstable behavior. So the existence of or composition of this the stable or unstable fixed points can be related complex behavior or the other classes. In this direction, Macintosh years ago establishes that following, for example, the graph theory across of the Bruijn diagrams, you can recognize complex behavior across of the number of cycles in the diagram, where the diagrams are interconnected with several kinds of diagrams, cycles, sorry, and how this interconnection between cycles relate complex patterns in the cellular automata in study. Okay, I consider particularly the case of Rule 22. Rule 22 is classified as a chaotic automaton, but at the same time, Rule 22 has a special characteristic because it is the projection in one dimension of the game of life. Particularly, the Rule 22 has some properties. For example, the future of the system is completely determined for the initial state, is sensitive of the initial conditions. This has very high dense periodic orbits that is related to attractors and establishes a kind of aleatority. How Rule 22 is related to the game of life? Because the rule display the same properties. For example, conditions where rule several central cell give born. The condition where the central cell give survival in the next time, and the condition where the date is established for the rest of conditions. In this case, we can see, for example, if we start with one cell alive in the initial condition and applying the rule 22, the dynamics in the evolution display fractal behavior, where the fractal behavior construct the Sierpinski triangles, and how these fractals propagate in the evolution space, and how they interact to preserve the same kind of information. Sometimes when you lost the parity distances between cells in the evolution space, this interaction of fractals produce chaos. And of course, it's very difficult to recognize some complex behavior in this rule, because the behavior is only related to chaotic regions. Well, what happens if we apply the mean field approximation for Rule 22? Well, the equation tells you that an stable fixed point is approximate to 42% of live cells in the next generation. It is the behavior to a long time in the Rule 22. However, the game of life displays two stable fixed points. The first stable fixed point is in this value that is 37%. That is a long time stability for the rule in the game of life. However, at the same time, the polynomial established an unstable fixed point in the 19%. This mixture of fixed points produce the complex behavior in the game of life. In the first instance, Rule 22 has not this combination of fixed points. So this implies that Rule 22 is chaotic in this approximation. However, what happened calculating the Bruijn diagrams for Rule 22? Well, here we can see how a lot of different cycles are interconnected. And these cycles represent regular expressions. that is very useful to codify the cellular automata spaces. In this case, we consider 2 cycles, well, 3 cycles, and codify the initial condition for rule 22 that produce a combination between periodic behavior and explosion of chaos. But how, in other cases, produce the analysis of complex patterns emerging in rule 22. If extend the analysis for more large strings in the rule 22, we can see how this composition of strings produce, of course, trivial periodic behavior where they interact and produce complex behavior. Of course, it's not trivial how recognize the complex behavior because maybe it's not evident how the particles emerge in these evolution spaces. However, we can explore the rule 22 using the symbolic equations and start a systematic analysis, testing several of these equations to explore particular initial configuration in rule 22 that produce eventually some kinds of complex behavior. The second case of the study is the rule 126. The rule 126 is considered a chaotic rule from Wolfram's classification, and the behavior is not identical to rule 22, but is similar because as a chaotic rule, it is able to produce fractals in the evolution. However, the density to produce chaos in few steps is more high than rule 22. Again, studying with the mean field approximation, we can see that the rule 126 has a stable fixed point in the 66%, and we cannot see any evidence of complex behavior in this rule. Okay, we will use a technique based of memory functions. Memory functions are useful for other scientific fields. For example, in the study of finite state machines, we can see historical systems. For example, deterministic finite automata, non-deterministic finite automata. They are systems that not need any memory in the system to work. And they, however, they are very powerful because you can study several complicated problems using only some megabytes in the algorithms. But you can, for example, analysis terabytes of information across of one algorithm determined for one deterministic finite automata, but the algorithm use only some megabytes and don't need more memory capacity. However, it is not the same for push-down automata, for example, or Turing machines, or some equivalent Turing machine, because these systems are historic systems, and they need remember what is happening in the system. In this case, the megabyte increase with the number of that type that is in the algorithm. What is the idea in cellular automata? Well, the idea is that you will remind what is the history in the evolution of the cellular automata, because this function consider 1, 2, 3, or n steps backward and establishes an intermediate a medium state where this step will storage what is the history. Later, selecting this kind of memory, you will be apply again the local rule and calculate the next configuration, the next global configuration. This process is iterated every time, and of course change the evolution of the local rule in the study. This idea was proposed for Ramon Alonso Sanz, a Spanish cellular automata researcher that is working with this idea for several years. So, what is the consequence to use memory functions in cellular automata? Well, in the first instance, we can remind a lot of the process in the evolution. And later, we can project this effect of memory in the future. That implies to try to recognize some kinds of dynamics in the original rules. But this is the exercise we will see now. Okay, it is a schematic, simple representation of the difference between the classic cellular automata and cellular automata with memory. The classic evolution consider every array where the local rule is selected simultaneously in the array and calculate the next evolution. In the memory case, we will remember some steps after, and later we will produce an array that is the memory that is not displayed in the evolution, only is hidden in the process. But later, in this array that store the memory effect, apply again the memory the local rule, the original local rule, and produce the next time. This double step, of course, has a price in the evolution because we need 2 times to get the next step. Of course, it's a bit more slow. Okay, what happens if select different levels of memory? In this case, tau represents the number of generations that we remember. For example, tau 3 implies that we will remember 3 steps to get the new generation. Tau equal 4 need 4 generations to calculate the next one. And we can use any number of values for tau. Of course, in this case, we select the majority memory. The majority memory is the conventional majority function where the most large frequency of a value in this history is the final result. For example, if the previous history is 0, 1, 1, the result is 1. But if the history is 0, 0, 0, the result is 0. Okay. However, we will put attention with tau is equal 4 because the evolution rule display gliders, and we expand the initial condition and filter the evolution for rule 126 with memory. We can see how exploit in gliders, glider guns, store lives, and how they collide in the evolution. the activity of complex behavior is very high for this rule, but this is particularly interest for use. And we have enumerated a lot of reactions with the particles in Rule 126 with memory that is very ample on diversity. So that is a very good candidate to try to exploit some computable system in the evolution. So with this number of reactions, we will produce or control collisions between particles to produce, for example, in this case, the implementation of logic gates. So we have implemented the NAND gate, where the NAND gate is a universal logic gate, where the binary value here is determined for the number of gliders concatenated. In this case, if we have in the final result of the collisions, a single glider represents the binary value 1, but in other case, if we have two gliders together, and then represent the binary value 0, so in this way, we can consolidate more and more complicated process in Rule 126. At the same time, we can explore another complex dynamics of the problem of self-organization in Rule 126 with memory, because we can see how across of multiple reactions, we can produce the glider guns in this automaton, where the glider guns has the self-interest because the glider guns relate the problem about of illimited ground in a cellular automaton. And the diversity of glider guns in this rule is really interesting and ample. Okay, what happened with Rule 22 with memory? Okay, again, selecting the majority memory and tau equal 4, we can see that Rule 22 with memory exploit in complex behavior. The dynamics is different to Rule 126. However, the reaction is very interesting because the number of reaction for two particles is significant here. By a consequence, we can control a lot of reactions, and indeed, we propose a scheme to handle the Franklin gate in one dimension with this rule, and we can control the position, the specific position for every particle, and establishes what is the phase where every particle starts in the initial condition, and produce the final result, that in this case is preserve the computable process and the final interaction. So the main interest here is how the memory function change the dynamics of elementary rules. Okay, we have three classes of dynamics in cellular automata with memory. A strong class refer what are the local rules that transform quickly using a kind of memory function. In this case, if you select any kind of memory function, the rules always change to other class. However, for the moderate class, sorry, this implies that if you select a kind of memory function, probably change to the dynamics, but not always. It is an average measure where the rule could change or not change. It's the dynamics. The weak class imply that the evolution rule don't change the dynamics. The dynamics preserve exactly the same behavior. Okay. Later, to study the 88 local rules in elementary cellular automata, we find that the rule 130 is a universal class. What means this? This means that if you take the rule 130 and select a kind of memory function, it is able to change to uniform class, to periodic class, to chaotic class, and complex class. Because this class is this rule is able to change to any other class, only selecting a kind of memory. These diagrams represent graphically what happens if you start, for example, the rule 54 is for Wolfram classification is a complex rule. But if you select a kind of memory, the rule 54 could change to class 1. This implies that the rule 54 has elements where the behavior could be is uniform. All right, but at the same time, if you choose another kind of memory function, the rule 54 has elements of periodic behavior. So this way, we can analyze the whole set of elementary cellular rules and determines the memory effect in every rule. Finally, we can see that the complex behavior is ambiguous. Well, any class is ambiguous because you can change to other behavior, selecting a kind of memory. And finally, in the universe of memory functions, you can change to any other, right? So that is a result that Kulik and you has discussed several years ago. This way, any classification that exists in elementary cellular automata is not final. Well, to the end my presentation, I will comment quickly the recent result, how you can construct complex cellular automata. It is a method very interesting because actually we can construct complex behavior with reversible cellular automata, where you can use dozens of cells or hundreds of cells. And the method is not complicated because you can choose, for example, an automaton with periodic behavior that is determined for a composition of 4 states, and later composed with other automaton. That is, in some kind, is related to the work from Sukanta, where they compose elementary rules to get a reversible behavior. But here, the product between two or more automata produce complex behavior. The only condition here is that you will consider one rule with periodic behavior and other rule with chaotic behavior. Because the product of this automaton that implies more states with reversible properties produce complex behavior. And the number of possibilities to get complex behavior increase very quickly. So I invite to see these rules. And of course, it is a new universe to the complex behavior in these kinds of reversible cellular automata. So thank you very much for your attention, and if you have any question, I will be very happy to hear you.
Thank you so much, sir, for the nice talk. It was so interesting. So, I think Sir has some question. Sukanta, sir?
No, so maybe some other may have some questions.
Okay. Please.
So I have, also its talk is very exciting. So I have one point. So you have talked about hard chaos and soft chaos, right?
Yeah.
Okay. And so is there any mathematical definition? So hard chaos and soft chaos?
You refer this kind of memory class? Sorry, because I cannot understand well what is your first word. Or I don't know if you can help me, Kamalika, to understand well the question.
Sir asked whether there is any mathematical definition to differentiate between hard chaos and soft chaos.
Okay. All right. Yeah. Sorry. Yes, thank you. Well, this reclassification comes from Andrew Wenshi. Wenshi say that several automata are class, for example, but some rules are more hard chaotic than others because the number of ancestors is more dense than others. So in this measure, if you have a tree with a very high dense of ancestors, when she say that it is a more hard chaos than not in other chaotic rules. That, for example, the rule 18 is not more hard than rule 90 for the density of ancestors in the in this basin of attractions.
Okay.
Hello.
Yeah.
Hi, Sumita.
Yes. Hello. Well, I wanted to know, as you increase the memory, that is tau, it seems that it changes the. So if it's increased when you start from the first step, for suppose tau is 4, then how well this mu will also change, because for the first case you don't have 4 memories. If the from the initial state, when you go on, after you have the 4 steps, then only you can use all these 4, isn't it?
Yes, you are right, Sumita. Indeed, a problem with this value of tau is that we have explored, for example, values between 3 and 20. But a consequence to increase the value of tau is that dynamics
Changes.
yes, but converge to trivial dynamics. So for
Yes.
exploration, number 4, 5, 6, 7, including 8, offers interesting behavior in complex dynamics.
And till tau is 8, that's what you want to say?
Yes, some rules has the capacity to display complex behavior. Some rules, not all.
Okay. Thank you.
Thank you, Sumita.
In Jam, you have a question.
Yeah, may I? Yeah. Thanks very much for that very nice talk.
Hi, Raman.
I learned a lot. Yeah. So I have 2 things. One is from, finally I still have a kind of very generic thing of, so what is the right model for a complex system? I mean, what's the right memory definition? There seem to be a lot, and they're all interesting, but what would you say? This is one. And the other is, the kind of memory definitions I saw remind me a lot about the way in game theorists talk about in the context of discounting, geometric discounting, or memory in strategies when there is repeated or games of infinite duration. So in general, I find that, I mean, I'm more from not cellular automata, but from automata theory background, and any kind of continuous valued memory models are very hard to obtain. And you seem to have very interesting ways of coming up with continuous valued memory. So I just want to know if there is some relationship, or it's just something that looks superficially. So yeah, thank you very much.
All right, thank you for the interesting question. It is difficult that you are asking, but this theory is with few analysis really, because actually our study is concentrated to determine where is the best memory function to get complex behavior. But of course, you can change the memory function. For example, I use with most frequency the majority memory. But however, you can sub parity memory, minority memory, or compose another kind of function. For example, another kind of mathematical function. For example, a Fibonacci sequences that can be implemented as a memory function that affect the history in evolution of cellular automata, and to get another behavior. The consequence, what is here? That the possibilities is an infinite possibilities to change the memory function. So, of course, remembering some studies about indeed for the same Camelita or Sukanta, what is the ancestors in this automata? Because, for example, the rule 126 with memory implies a non-deterministic relation in the history of the evolution. The consequence is a very high number of ancestors in the evolution. That is very difficult because what is the decision to determine what is the evolution for this node? But the study is very early, and several techniques to formalize the consequence of in this memory effect are very welcome for the Cellular Automata Indian community, are very welcome.
Thank you very much.
Thank you.
Okay, anyone else?
Sir,
Yeah. Sukrit.
yeah, I want to ask a
Supredi.
question. Yeah, hello, sir. Sir, actually, I wanted to know that by weak chaos, so you mean that there are less number of periodic points which are dense, right? I mean, I can't understand the difference between weak chaos and strong chaos.
Oh,
I
yes.
mean, how can you distinguish these two Cs, cellular automata?
Okay, thank you. Um, it is, again, it is in certain kind subjective because, as comment with Sukanta was some seconds ago, Andrew Wenshi say that if you calculate the attractor tree for the evolution, for example, the density of the evolution, if the density is high, or, that implies many relations in every level of the tree, you can say that it is a hard attractor, a hard chaotic rule. But if the density is not high, that implies that you have more levels in the tree with a number of ancestors in every level, but is not dense. Then it is a chaotic rule, but not hard chaotic, because the hard chaotic implies more relation in the same level for the tree. It's more dense. But actually, it is only a measure that Andy Wenshi has discussed in the recent years. But however, don't exist a formal proof then establishes it is hard as it is not hard and it is weak chaotic rule, because the approximation is statistical. Then, of course,
Okay.
for example, for the complex behavior, is the same problem. We can say that rule 54 is more chaotic than rule 110. If we use the Epstein definition, maybe rule 10 is more chaotic than rule 54 because the family of gliders is most few. However, if you analyze the evolution of rule 54 and rule 110, it is more the probability to get homogeneous behavior in rule 110 is more high than rule 54, because in rule 54 you can analyze or see 100 or 1,000 of steps, and the evolution no converge. That is most frequent in rule 110, for example. But in a formal definition with a theorem or corollary, don't exist any theorem that implies that this complex behavior is more hard or less. So it is the same problem for chaos. So this proposition about of hard or weak chaos is ambiguous as well.
Yeah, yes.
But however, the probability gives a kind of approximation that has worked for Wenshi, Hector, Gurtowicz, Macintosh, Wolf and Self, but a theorem that is this rule is hard chaotic or weak chaotic don't exist. Right?
Thank you, sir.
Thank you.
Okay, anyone else? Okay, I have a set of questions to you.
Yes, you are very welcome, Sonali.
Yeah, sir, you have done the classification of CA with memory that all these things are based on space-time diagram, like you have to see and then you have to classify, or you have some mathematical background as well. That is one question.
Okay.
Yeah.
The diagram only illustrate what is the
So,
transition between rules for the memory function. But the memory is only using three kinds of memory: majority, minority, and parity.
hmm,
Of course, you can use
hmm,
many other functions of memory, including probabilistic functions with memory,
hmm,
and probably the relations could change. But our interest in this study is only proof that the complexity is ambiguous, where you can change the dynamics between the all dynamics.
hmm,
So in this case, for example, if the rule 130 is able to transit for the all classes, so rule 130 has property or has properties of class 1, class 2, class 3, and class 4.
hmm,
So again, uh, any study don't work in this aspect.
hmm. Okay, okay. But my question was whether you have to find that behavior just by watching the evaluation, just like Stephen Wolfram did, or is there any mathematical tool also that can theoretically say that it will change its behavior from this class to that class? Is there something possible, or you have to just see its evaluation and then you can decide
Okay, you are asking about of the last slide?
about the classification? Yeah,
Yes, okay. Uh,
about the classification you are showing there. You are showing the space-time diagram, no?
okay,
So we have to see its behavior, the dynamics, and then we can decide.
okay,
Or is there any parameter?
okay. Uh, we use two algorithms to decide reversibility. Um we use the cycle diagrams where, well, you are expert in reversible Cellular Automata, but the cycle diagrams is only if you find cycles in the attractor. The other technique is using the Bruijn diagrams, where the Welch
Yeah.
indices establishes that the evolutions reach two indices, the Welch indices, where the vertices converge in these vertices. So you have a reversible Cellular Automata. So to get more bigger reversible rules, we compose, for example, two reversible cellular automata with a Cartesian product, and we produce another much bigger reversible cellular automata. So, of course, when you use few cells, the dynamics is not complicated. Frequently, the reversible dynamics is periodic, as Rule 15, for example. No, but if you use more states, the dynamics change in reversible systems. For example, then Kenichi Morita, Norman Margolius use reversible two-dimensional cellular automata with many states. So the universe of reversible rules is at the same hue. In this case, you can see the Wolfram classification only in reversible rules. So, of course, trying this composition of reversible rules, where you can distinguish, for example, chaotic or periodic behavior, if you compose these dynamics, it's very probably that you will get complex dynamics.
Okay.
It is the conjecture now. Indeed, not only in reversible rules, in any rule. Right?
Okay.
Okay.
Thank you. Okay. Another question is whether there is any connection between this CA with memory and without memory. Like if a CA with memory, CA without memory can simulate the behavior of CA with memory. Is there any connection, something like that, just like it has in asynchronous CAs?
Oh yes, yes, yes. Of course, the memory function always is uh, 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 um, a consequence of the systems, because in the nature or in the universe, we can think that the systems are working in parallel and maybe not correlated or connected with them. However, to very long time, the memory works because it's, for example, what happened in our heart. Of course, when for example, what happened with the people that living 4,000 years ago? Where is the body? Where is where is the element of this person? It is recycled. Recycled. No, that we will. This action is repeated every year with all living organisms. So our body is composed for other elements that has an existence in the earth and the universe, and it is it's a well, right?
Okay.
So
Okay.
of course, in formal systems, for example, Turing machines or automata, uh, Turing machines don't exist if the memory function works in the system.
Yeah.
So, for example, when you are controlling a Turing machine in the game of life or a cyclic tax system in Rule 110, you need a kind of memory in the system
Yeah.
to remember the data in the process. So it is very interesting because For example, Rule 110 is an historic system. It cannot remember the process. However, when you implement a cyclic task system, consequently, Rule 110 is able to remember the process across a finite state machine. So you are composing two systems in only one, right? So for this reason, it is very useful and powerful implement computers in cellular automata, because you can control an infinite of computable process in the automaton.
Okay. So have you thought of it like implementing computer using cellular automata?
Yes, 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 yes. Yes, indeed. We can think how, Wolfram Cell say that the universe is a composition of several small computers connected,
Yeah.
working together. Yeah? That if you remember, it is back to the concept of symbolic equations. Because if you have a regular expression, what is the most small element of a regular expression? The alphabet, right?
Hmm.
The alphabet is the most small symbols of a regular expression. But if you construct a very large regular expression, complex regular expression, all they are subsystems of the alphabet.
Hmm. Is it?
So automata, several automata is the same. It's the same.
Okay.
The game of life
Yeah.
is a composition of small automata,
Hmm.
and so on, right?
Okay. Yeah. Okay. So last thing is, sir, you are showing one method to generate complex CAs. There you were using random expansion, but it will increase the number of states. No, then how have you? Are you reducing the number of states also, or it will be just the number of states that will come out of expansion?
Okay, it is interesting again. Um, for example, Rule 22 with memory
Hmm.
shows a complex rule only with two gliders.
Hmm.
That is completely different to Rule 110 or Rule 54.
Yeah.
Indeed, when you explore the game of life, you can see a very large number of gliders. But Rule 22 with memory use only two gliders. But the interesting point here is how across of these two gliders, you can construct a computer.
Yeah.
So it is very interesting for me because it's remembering old problems about of universal Turing machines.
Hmm.
For example, Turing proved that universal Turing machines was constructed with I don't remember very well, but maybe with 18 elements in the alphabet or states. Mhm. But Shannon conjectured that a universal Turing machine could be exist with two symbols and two states, right? So in this case, for example, with Rule 110, Rule 110 is the most small cellular automata able to simulate a computable system with only 8 relations, right? However, the problem with Rule 110 is that you have 18 gliders in the universe of Bruijn. But some of these gliders are infinite because they grown with an infinite number of extensions. So the consequence is that you are working to an infinite problem. However, with rule 22 with memory, you have not this problem of infinitude because these two gliders interact. Of course, that is interesting. What is the number of interaction between these two simple gliders? And with Kenichi Morita and Adamaski, we have constructed computable systems in this automaton, and we can understand how the memory was very useful to get this very simple automaton only with two states and two gliders. And we are working now to try to implement equivalent Turing machine with this automaton.
Okay.
So all yours are very welcome to this project.
Thank you so much, sir. Thank you for the nice talk and then tolerating all my questions.
I am very happy to have contact with you with this very interesting book. I know very works for Cellular Automata Indian community that is very interesting, very formal, and I have always interest for the work of Sukanta for several years. He
Thank
is a great professor in this area.
So thank you, General, for coming and giving so much talk. And you have always encouraged me, in my several talks. We talked, I mailed you several times and you always encouraged me. Okay. Thank you so much for your encouragement and all our inputs.